Hello, everyone. In this video, we're going to look at the Claisen condensation mechanism. This is a reaction similar to our aldyl addition reaction, but it occurs with our ester. So we'll start out with an ester instead of our carbonyl, and we're going to react it with a alkoxide. We're using our alkoxide as a strong base in order to deprotonate our ester and form the carbonyl, or the enolate. So we have our alpha hydrogens next to that carbonyl. This is the site where we'll be reacting. So our first step, we're going to deprotonate to form our enolate. So this will lead to our enolate. I'm showing it here with our major resonance structure with the negative charge on the oxygen and our double bond. Our alternative resonance structure would, of course, have the negative charge here on our carbon instead. Once we have our enolate formed, so here's our enolate intermediate, we now have the opportunity to react in essentially a nucleophilic acyl substitution reaction. So we're going to add this enolate onto a second equivalent of our ester using kind of our standard nucleophilic acyl substitution mechanism. So we take another unit of our ester, and now we're going to attack our partial positive carbon here. So bring our electrons down from the oxygen attack using our nucleophilic carbon. And our nucleophile, of course, attacks that electrophilic site here by our carbonyl carbon. Now we're going to move our electrons up onto the oxygen again, and this will create our tetrahedral intermediate. So we're going to add on next to our carbonyl. So we've now linked our compounds together here as we form our Claisen condensation product. Now this is a tetrahedral intermediate, similar to what we would see in a typical nucleophilic acyl substitution reaction. So now we can bring down our electron from that tetrahedral intermediate and kick off our alkoxide leaving group here, right? So this is very similar to the second step that we see with our nucleophilic acyl substitution reactions, where again, you form that tetrahedral intermediate, and then you're kicking off a leaving group in order to create your product. So that will kick off our leaving group, and we'll end up with now our aldyl addition product, or Claisen condensation product, rather. So we have one complete unit of our ester. And then attached to our alpha carbon here will be just the carbonyl half of our other ester. So we've essentially replaced the alcohol portion with our second unit of ester, and we still keep that carbonyl portion of the ester here. So these electrons were coming down to reform that double bond. That's what ends up here. And we kicked off our alkoxide. So we also get our alkoxide. Now at this point, all of these steps are reversible. So we could push the reaction backwards in order to get our original reactants. In order to push this to our final products and make sure that we don't just reverse the reaction, we're going to use acid to, or we're going to use our ethoxide rather to deprotonate the product here. So we can form a new enolate. Along with our alcohol from that alkoxide. This deprotonation here to make our enolate is effectively irreversible because our alkoxide is a very strong base. And in this case, our alpha hydrogen here between those two carbonyls is actually relatively acidic, right? So we have an acidic group and we have our strong base here, which makes this step strongly favorable and push strongly towards our product here. If we want to isolate the actual the ketone form instead of the enolate, we can just add acid in the second step in order to isolate our final product. So this is our full mechanism. A couple things that we should note to end. So our alkoxide needs to match the alcohol that's used in our ester, right? Because this alkoxide can also attack our ester in a nucleophilic acyl substitution reaction. And so if we don't match our alkoxide to the structure of our alcohol, you'll end up with a mixture of products due to that alcohol both attacking and forming the enolate and that alkoxide attacking and replacing the alcohol. So if we wanted to, if for example we use a ethoxide instead of that isopropoxide that I used to match the alcohol group from our ester, so I'll quickly show you what would happen if we didn't match it. So let's say we took the same ester and we add ethoxide. So we could, of course, react as usual with that alpha hydrogen to get our enolate, but we can also just attack here in a nucleophilic acyl substitution reaction. We'll attack, move our electrons out of the way. And we end up with our tetrahedral intermediate, which can now eliminate the leaving group and produce a different ester than our starting ester. So we use this simple nucleophilic acyl substitution reaction. We end up with now a new ester, which will react to create different products in that Claisen condensation reaction. So here we would end up with multiple products forming. because we would have this ester that would react. We would also have our original ester that could react in the Claisen condensation reaction. And so you'd end up with just a wide variety of different products that would reduce the yield of your desired product. So we always want to make sure that you have the same alkoxide structure as the alcohol from your starting ester. So again, overall in this reaction, it has a similar mechanism to the aldol addition reaction for the first part, but then the second part, we actually do almost a nucleophilic acyl substitution reaction where we're replacing the alcohol portion of our ester with the enolate from our second unit of ester.